Now that we have looked at naming molecules and drawing Lewis structures, next we'll use Lewis structures to determine bond polarity, molecular shape, and intermolecular interactions. To determine bond polarity, we need to know the electronegativity of an atom. Electronegativity represents how much an atom pulls electrons towards it. Although carbon and oxygen in carbon dioxide share electrons, oxygen is greedier for those electrons because it has a higher electronegativity value. Electronegativity increases from left to right across a period on the periodic table. It decreases from top to bottom. So nonmetals have high electronegativity values, with fluorine as the highest, while metals have low electronegativity values. Note that the trend for electronegativity matches that for ionization energy. The electronegativity values will be provided for you, so you do not need to memorize them. When bonding electrons are shared equally, as in hydrogen, the bond is a non-polar covalent bond. But when bonding electrons are shared unequally, as in hydrogen chloride, the bond is a polar covalent bond. We use the difference in electronegativity values between the bonding atoms to determine bond polarity. When the difference in electronegativity between bonding atoms is from 0.0 to 0.4, the bond is nonpolar covalent since the electrons are shared equally or nearly equally. When the difference is from 0.5 to 1.8, the bond is polar covalent since the bonding electrons are shared unequally. When the difference is from 1.9 to 3.3, the more electronegative atom completely attracts the electrons towards itself, making the bond ionic. Because of the huge difference between 1.9 and 3.3 in electronegativity between metals and nonmetals, we can say that as a general rule, when metals and nonmetals react, they form an ionic compound. As the electronegativity difference increases, a polar covalent bond becomes more polar. Since electrons are shared unequally, one atom has more bonding electrons and more negative charge, while the other atom has less electron density and more positive charge. The separation of charge that results from the unequal sharing of electrons is called a dipole. The positive and negative ends of a dipole are located by using a lowercase Greek letter delta with a positive and negative charge, and an arrow that points from the positive to the negative end of a dipole. Here are some examples of compounds for you to practice predicting bond type using electronegativity differences. You can block this as you practice. First, determine the electronegativity difference. You can use the difference to predict the type of bond and the type of electron sharing. Lastly, you can figure out the bond dipoles. Once you know the bond dipoles and Lewis structures of molecules, you need to determine the three-dimensional structure of molecules to predict the overall polarity of the molecules and intermolecular attractions. A theory that helps to predict the three-dimensional shape of molecules is called the valence shell electron pair repulsion theory, which is a mouthful, so we use VSEPR instead. It describes how electron groups are arranged around the central atom. Note that a single bond, one double bond, one triple bond, and one lone pair all count as one electron group. According to valence shell electron pair repulsion theory, the specific shape of a molecule is determined by the number of atoms attached to the central atom. In this class, we need to know how to predict the molecular shapes of 6 types of molecules. We will look at each of them in detail. First, draw the Lewis structure for the molecule. Second, determine the number of electron groups around the central atom. Recall that one double bond counts as one electron group. Third, determine the electron group geometry. For carbon dioxide, the repulsion is minimized by placing the 2 groups on opposite sides of the carbon atom, giving the molecule a linear arrangement with bond angles of 180 degrees. Lastly, determine the shape based on atoms around the central atom. Exclude any lone pairs. For carbon dioxide, the shape has a linear molecular geometry where the 3 atoms are in a straight line. For formaldehyde, refer to the previous video to determine how to draw the Lewis structure. There are 3 electron groups around the central atom, 2 single bonds and 1 double bond. To minimize electron pair repulsion, the 3 electron groups orient themselves at 120 degrees around the central carbon atom. The shape with 3 electron groups around the central carbon atom is called trigonal planar. Note the prefix tri for 3 and planar because all the atoms are in the same plane. For SO2, determine the name. Refer to the previous video if you need a refresher. Draw the Lewis structure for SO2. There are 3 electron groups around the central sulfur atom, 1 lone pair, 1 single bond, and 1 double bond. To minimize electron pair repulsion, the 3 electron groups orient themselves at 120 degrees around the sulfur atom, forming a trigonal planar electron group geometry. And for molecular geometry, look at the shape of the atoms, excluding the lone pair. The 3 atoms are in a bent shape. To determine the shape for methane, first you draw the Lewis structure and then determine the number of electron groups. Methane has 4 electron groups, all single bonds. To determine the molecular geometry, look at the shape of the atoms. The shape with 4 bonds on the central atom is called tetrahedral. You can also represent the structure in wedge dash notation, where the solid line is in the plane of the page. The wedge or bold bond is coming out of the plane of the computer, while the dash is going away from you. For ammonia, again draw the Lewis structure, and there are 4 electron groups around the central nitrogen atom, 3 single bonds and 1 lone pair. To minimize electron pair repulsion, the 4 electron groups orient themselves around the nitrogen atom, forming a tetrahedral electron group geometry. Finally, to determine the molecular geometry, look at the shape of the atoms, excluding the lone pair. The shape with 3 bonds and a lone pair on a central atom is called a trigonal pyramidal. Note the tri for 3 atoms around the central atom and the pyramidal because it looks like a triangular based pyramid, or like the legs of a tripod. For water, draw the Lewis structure, and there are 4 electron groups around the central atom, 2 single bonds and 2 lone pairs. To minimize electron pair repulsion, the 4 electron groups orient themselves around the oxygen atom, forming a tetrahedral electron group geometry. To determine the molecular geometry, again look at the shape of the atoms, excluding any lone pairs. The shape with 2 bonds and 2 lone pairs on the central atom is bent. Here's a look again at the 6 molecular geometries that we will look at in this class. Practice using the 4 steps outlined in the previous slides. First, draw the Lewis structure. Second, determine the electron groups. Third, predict the electron group geometry. And fourth, figure out the molecular geometry. Now use VASPER to determine the name and molecular geometry for H2S. Using the 3-dimensional structure of a molecule, we can determine the overall polarity of a molecule as well as the forces that hold the molecules together. To determine if a covalent molecule is polar or nonpolar, ask yourself the following questions. First, are the bonds polar? If not, then the molecule is nonpolar, as in hydrogen. If the bonds are polar, ask the second question. Do the dipoles in the molecule cancel each other out? If they do, then the molecule as a whole is nonpolar. An example is carbon dioxide. If not, the molecule is polar, meaning one end of the molecule has more electron density than the other end, as in hydrogen chloride. Determine whether the molecule OF2 is polar or nonpolar. First, analyze the problem. We are given the molecule OF2. We need to determine the polarity of the molecule. In order to do that, we must first draw the Lewis structure and determine bond polarity. So first, determine if the bonds are polar covalent or nonpolar covalent. OF2 contains 2 oxygen-fluorine bonds. The electronegativities for oxygen and fluorine are 3.5 and 4.0 respectively. The electronegativity difference is 0.5, which is greater than 0.4, making the OF bond polar covalent. If the bonds are polar covalent, draw the Lewis structure and determine if the dipoles cancel. A molecule with 4 electron groups composed of 2 single bonds and 2 lone pairs is bent. This is the same shape as the structure of water. The 2 dipoles do not cancel, therefore OF2 is a polar molecule. Knowing the overall polarity of molecules helps us determine the intermolecular forces that hold the molecules together. Remember that unlike charges attract each other. So since polar molecules have net dipoles or charge separation, the positively charged end of the dipole in one molecule is attracted to the negatively charged end of the dipole in another molecule. These are called dipole-dipole interactions. A special type of dipole-dipole interaction is called a hydrogen bond. This results when a hydrogen atom bonded to a fluorine, oxygen, or nitrogen interacts with a lone pair of fluorine, oxygen, or nitrogen. These are the strongest intermolecular forces, and they are responsible for holding your DNA together. To remember these atoms, think chemistry is fun. F for fluorine, O for oxygen, and N for nitrogen. Even for nonpolar molecules which lack permanent dipoles, there is still slight unsymmetrical distribution of electrons as molecules bump into each other. This creates temporary dipoles. These weak attractions in nonpolar molecules are called dispersion forces, and they are the reason even nonpolar molecules can form liquids and solids, which need forces to hold them together. The strength of intermolecular forces determines the melting points. Melting requires energy to break the forces holding the molecules of a solid together. The greater the intermolecular forces, such as hydrogen bonds, the greater the melting points. Ionic compounds, which are held by strong ionic bonds, have very high melting points. Here is a summary showing the comparison between the type of bonds and the strength of attractive forces. This marks the end of chapter 6. We have learned about how atoms react to attain stable octet configurations. They do so by transferring electrons, forming ionic compounds, or by sharing electrons, forming covalent compounds. We learned how to name compounds and how to derive the formulas. Lastly, we learned how to use the bond polarity, molecular shape, and molecule polarity to determine the attractive forces that hold molecular compounds together. Please come to class on Monday with questions about any concepts that need further explanations. And as always, happy studying.